Continuing with the B course, in the last session it is not possible to finish the B course properly. Now we continue with a little bit review of B curves, then we'll move to the capability curves. B curves of a synchronous generator. Then we know that the conditions for drawing the B curves is that the generator which is connected to infinite bus feeding the constant power, and the infinite bus V is constant, and the generator is represented by source of voltage and a synchronous reactance Xs, neglecting the resistance Ra. If the power delivered to the infinite bus is constant and the infinite bus voltage is constant, then the I cos phi is a constant. If you are transferring V to this, then P by V is a constant, therefore I cos phi is a constant. Then another conditions also we are derived here using the power angle equation. P is equal to EV by Xs sin delta, in which P, V and Xs are constant. Therefore, E sin delta is a constant that is given by P Xs by V. Means the locus of IA is the same because the IA cos phi is remains same, and at the same time the locus of E is also in the straight line. Okay, that we are drawing here. Then we have to draw the vector diagram for the alternator which is connected to infinite bus. The B is the infinite bus voltage, and the current which is delivered to the infinite bus is the first I am considering the unity power factor. Then if we are adding the IAXs to V, so that I am getting the value of generated voltage. Therefore, I am considering here unity power factor. For unity power factor, current and voltage are in phase. Then I am adding IAXs. Then what I am getting is the generated voltage E. Here E2 is the voltage corresponding to unity power factor. Then the corresponding to unity power factor, the excitation is called as the normal excitation. It is called as normal excitation or 100% excitation. Now what I am doing here is, now I am decreasing the excitation. Means it is what I am calling is decreasing the excitation. Means it is what you are calling is under excitation. It is under excitation. If we are decreasing the excitation, what happens to the voltage? Voltage is decreasing. Therefore, the voltage is decreased from E2 to E1. Here what I did is, I am decreasing the excitation, means it is under excited. Then how to get the generated voltage from the terminal voltage? You have to add IAXs so that I am getting the value of E1. For corresponding value of E1, my IAXs is thus, that is I1 x1 is this value, that is to V. If you are adding this, what I am getting is E1. You can see here it is a locus of E because E sin delta is a constant that we are derived. Therefore, whenever there is a variation of the excitation, the generated voltage is moving all along this particular axis. So that when if you are decreasing the excitation, the generated voltage is decreased from E2 to E1 here. Then to get E1, what I have to do is I have to add IAX with V, so that I am getting here. This IAX should be perpendicular to current I, so that to get that particular I, it should be perpendicular. Therefore, what I am observing here is, because of the under excitation, the current IA is moving from the unity power factor to leading power factor. When the excitation is decreased, the current which is in the unity power factor, from the unity power factor it is moving towards the leading power factor. So that the one observation what we are observed here, when the excitation of the alternator is decreased from its normal excitation, the generated voltage is decreasing, then the current delivered to the load is the leading in the nature. Similarly, if you are increasing the excitation, then what happens? The generated voltage is increasing from E2 to E1. From 100% excitation, if you are increasing the excitation, E3 is increasing. Then how to get E3? To V, if you are adding IA excess, so that I am getting E3. Therefore, it is IA excess. IA excess. This IA excess should be perpendicular to the current. That is correct. Now, what we are observed here is the current now from the 100% excitation, that is from the unity power factor, it is moving into the lagging power factor. Lagging power factor. That is the other observation what we have seen here is if your excitation is increasing, the generated voltage is also increasing. At the same time, the current is moving towards the lagging in the nature. The lagging in the nature. Okay, these are the observations we are getting. That is for over excitation, the current is becomes lagging. For under excitation, the current is leading, and at the unity power factor, this is the what you are calling is 100% excitation. All these three, this is the locus of I. That is I is moving in the along this axis because it is I cos phi is remains same. If we are taking the cos component of this, once again this remains same. Okay. Now this is angle delta 1, delta 2. Now I am considering all these three cases here. I have drawn all the three. It is E2, E1, that is under excitation, E3 over excitation. For under excitation, current is IA1. Then current IA1, if the excitation goes on decreasing, the current IA1 is goes on increasing along this axis. That is what you are observing here is if you are under excitation, if the excitation is goes on decreasing, the voltage E1 is goes on decreasing. At the same time, the current I1 is goes on increasing in the leading nature. At the same time, when the excitation is increasing above its 100% excitation, then what we are observing is the generated voltage is goes on increasing. At the same time, the current is goes on also increasing, but it is in the lagging in the nature. This the conclusion we are drawn. The based on that, you have got here lagging, you have got a leading here. Therefore, you can draw the V curve from this particular data. That is, I will consider excitation is 100%. That is a normal excitation I am considering here. Therefore, for this 100% excitation, I am assuming that the generated voltage is 1.2. For 100% excitation, I am considering it is a 1.2 is the units of the generated voltage. Then the current corresponding to this normal excitation I am considering as 1. All or I am considering this the data that is for 100% excitation, it is 1.2, that is the generated voltage, and the current is the 1 unit. And for 100% excitation, we know that the power factor is unity, therefore the power factor is unity. Therefore cos phi is 1, therefore phi is the 0 here. The phi is 0 here. Then what is I cos phi? This I cos phi is 1. I cos phi is 1. But we know that I cos phi is the constant that we have derived already. If it is 1, the others is also 1 voltage. And at the same time, the terminal voltage is also the constant. Therefore, I am keeping it is 1, 1, 1 here. Now, next what I am doing here is I am decreasing the excitation from 100% to 90%. That is under excitation. For 100% it is 1.2. For 90%, what is the generated voltage? That I have to calculate. That is 90 by 100 into 1.2. It yields it is 1.08. We are getting that is for 100% excitation is 1.2. For 90% it is 1.08. Then the power factor what I am getting from excitation is decreased for 90%, then the power factor is it is moving from unity power factor to 0.9 power factor. 0.9 power factor. Then we know that the I cos phi is 1. I cos phi is 1. Phi is 0.9. Therefore, the corresponding value of I can be calculated. Because I know I cos phi is equal to 1. Cos phi is 0.9. Therefore, I can calculate what is the value of I. I is 1.11. If the power factor is 0.9, the corresponding angle is 25.8. What you are observed here? By decreasing the excitation, the voltage is decreased, then the power factor is going from unity to the leading of zero point 0.9. This is one example I am taking. 0.9 power factor is going to 0.9 power factor leading. Corresponding to 0.9, then 1 I cos phi is 1. From that I am getting it is 1.11. Further, I am reducing the excitation from 90 to 80%. Then what I am getting here is 0.96. That is the 0.96 is the voltage. Because for 100% 1.2, for 80% it is 0.96. Then I am assuming that by decreasing the excitation, then my power factor is moving from 0.9 to 0.8. That is I am taking it as a 0.8. Once again, Ia cos phi is 1. Cos phi is 0.8, therefore I is 1.25. What I am getting is 1.25. Then the corresponding angle is 36.8. Then what you are observing here, when the excitation is goes on decreasing, the generated voltage is goes on decreasing. However, the armature current is goes on increasing. At the same time, the power factor angle is goes on also increasing. Now, from the 100% excitation, I go on decreasing the excitation. That is, I am increasing the excitation to 110%. For 100% it is 1.2. For 110, that is 110 divided by 100. That is what I am getting is 1.32 is the voltage. Then, because of this increase in the excitation, my power factor is increasing to 0.9. I am considering here is it's a 0.9. Then once again Ia cos phi is 1, therefore Ia is 0.9 by 1 by 0.9, therefore what I am getting is 1.11. Therefore what I am getting here is there is an increase in the angle phi, that is 25.8. That is because of the increase in the excitation, generated voltage is increasing, then the power factor is changing from unity to 0.9 lag. Because of this change in the power factor angle, the current is increased to 1.11. Then further I am increasing the excitation to 120%, that is 110 to 120. Because of increase in the excitation, generated voltage is increasing. Because of the excitation is increasing, your power factor angle is also increasing to reducing to it is a 0.8. Then if for 0.8 power factor, my armature current will be 1.25. Therefore, the phi is increased to 36.8. These are the observation what I am getting here from the table. Okay. Look into this. How we are getting this? How we are getting this 1.11 I explained just now. That is, we know that Ia cos phi is equal to 1. Ia cos phi is 1. It is 1. Now, I have got a phi is 0.9. Therefore, Ia is equal to 1 by cos 1. That is 1 by 0.9. That is 1. This is how you have to calculate the value of this armature current. Okay. Now, what I am interested here is I want to draw the curve for field current versus the armature. Okay, field versus armature current. Therefore, this is the curve what I am getting. That is how we are getting that curve. You are getting the curve from these two. To look into here, for 100%, this is corresponds to 100% of the excitation. Means it is a 100% excitation. It is a 100% excitation. It is a 100% excitation. Then the power factor at this is unity power factor. Unity power factor. Unity power factor. The current what I am getting here is, you can call it is 1 here. This is what I am getting is, it is 1. That is the minimum current what I am getting here. It is 100% excitation. Corresponding to 100% excitation, my armature current is 1. Now what I am doing here? I am reducing the excitation. This is 100% here. Then if you are reducing means it has to come over here somewhere. Therefore, that is the unity power factor. Then if you are reducing the excitation means that is this is corresponds to 90%. Then for 90% of the excitation, what is my armature current? The armature current will be 1.11. Therefore, this is the point you are getting. The next point you are getting, further if you are reducing the excitation, means you are getting somewhere here, that is here I am getting, then the corresponding value of the current is 1.25 units and this is 80%. Then what you are observing is, when the excitation is less, the current is more. When the excitation goes on increasing and it is reaches 100%, the current is the minimum. Thereafterwards, if you are further increasing the excitation to 110%, then further there is an increase in the current. That is, you can see here. That is, you are increased to 110% from unity power factor, it is increased in this way. Further, if you are increasing the excitation to 120%, then it is moving to this point. Means what you are observing is, if it is 100%, the current is a minimum, that is the excitation. If the excitation is less than 100%, it is under excited. In that case, the current is goes on the increasing as the excitation is decreasing. Means the meaning of this is, when it is a unity power factor, it is neither absorb or deliver the reactive power. Whereas in the case of a leading power factor, that is what you are calling is under excited alternator, which is receiving the reactive from the infinite bus. When it is over excited, means the excitation is more than 100%. In that case, the nature of the power factor is a lagging. In that case, the alternator is delivering the reactive power to infinite bus. This is how we have to explain the vehicle of the machine.